Well, welcome. How was your break? It was nice. It's nice to be back, though, right? It was like summer yesterday, so it felt like a summer break almost. Okay. Well, hopefully you're here for computer architecture 447, and hopefully you're excited about it. We'll have a lot to cover in this course. It's a lot of exciting or fascinating material, at least for me. Hopefully you'll be fascinated like me too. It's going to be hard work, but I think as CMU students, you're used to that, so it should be fun. Okay. I guess let's get started. And I got the date right. So I hope you're here for this. What is that? Hopefully you've taken 213 or 243. Who was here long enough that it was 243? Oh, okay. I guess it's not that long ago, right? Okay. At some point, I'm going to get rid of this 243, I think, but not yet. In 213 or 243, you saw C as a model of computation, right? It was really your model, abstraction level. And you saw a programmer's view of how a computer system actually works. So C is a high-level programming language. Even though it's one of the lowest-level programming languages, it's still high-level. And hopefully you've taken something else, which is 240, which is the digital logic course or logic design course. And this was more of the bottom-up view of a computer, right? You saw digital logic as a model of computation, right? That was what computation was about. You put these logic gates together, and they computed something for you. It was not at the C level. And this was hardware designers' view of how a computer system actually works, right? Nobody actually, most programmers don't go place gates, and they don't program that way, right? You could do it that way if you have reconfigurable logic, and if you were programming at that level. So there could be programmers doing that, but most programmers in the world do not do that, and we'll get back to that. So you saw hardware designers' view of how a computer system works. So hopefully you have both perspectives right now. In this course, we're going to bridge the gap, which is asking the question, what happens in between these two things? What connects the programmer's view of a computer system to the hardware designer's view of a computer system? So what happens in between? You have this assembly program. C eventually gets translated to assembly. And it ends up somehow executing on this digital logic, right? These gates. And how does an assembly program end up executing as digital logic? Hopefully we'll answer that question throughout this course. And also from the bottom up, how is a computer designed using logic gates and wires to satisfy specific goals? What are those goals? We'll get to that later today and throughout the course. But one goal is to make sure that the programmer's goal is satisfied, right? If they want to solve a problem, that problem should be solved with these logic gates and wires. So hopefully you'll learn all of this. And I keep this picture in your mind in the entire course, because this is really the soul of computer architecture for me. The architect or microarchitect's view is, how do you design a computer system that meets these system design goals? And the choices you make, both in the hardware side and the low-level software side, as we will see throughout this course, and the interface side, which is what happens in between, critically affect both the software programmer up here and the hardware designer. So computer architecture, this course is listed under hardware, but this is really a hardware-software course together, because whatever you do at the interface, as well as underneath here, critically affects what happens up here, as well as what happens down here. You can make a choice here at the interface that makes programmer's life very, very hard. You can tell the programmer, I'm not going to execute your program fast. I'm going to execute it like a dog. Now it's the programmer's burden to write very high-performance programs, right? And we will see that this is a choice that has been made by some of the companies. Like you all know about multicore processors, right? One way of potentially improving system performance is by adding multiple cores or multiple processors into the system. An alternative to that is to design a much more powerful, higher performance core, right? If you have a much higher performance core, the programmer doesn't need to parallelize his or her program to get high performance. Whereas with multicore, you have these cores that are not necessarily high performance. Let's say they're simple, Now it's the programmer's burden to parallelize the program into threads to get high performance out of that hardware. So hardware designer makes a choice: multi-core, wimpy cores, slow cores. Now the software designer needs to somehow parallelize their program. Versus high performance core, now the software designer is happy. They just focus on features, perhaps, right? So this is one example. And throughout the course, we will see many, many examples of how these choices that we make at the architecture, interface, and the hardware level actually affect both the hardware designers, the software writers, and the hardware designer's job. Well, how does the multi-core affect hardware designer's job? Well, designing a simple core is easy, right? That's good for the hardware designer. That's good for the microarchitect. They don't need to do much. Whereas designing a high-performance core that can execute a single thread much, much faster, it turns out it's very, very hard. And we will see many techniques throughout this course, like out-of-order execution, dynamic scheduling, pipelining, caches, more sophisticated memory scheduling techniques that are needed to actually get high performance out of a core. And that makes hardware designers' job hard, right? And this is another fundamental thing. You can make the software programmer's job hard, hardware designer's job easy, versus you can make the hardware designer's job very hard and software programmer's job easy. Or you can try to find a trade-off that balances the easiness or hardness of the job. And we'll cover a lot of issues related to this. And I'd like you to have this perspective from the very beginning, because whatever we will study have implications across the entire stack. Make sense? So don't take this as just a hardware course. OK. Well, I said something in the end, stack, right? What is that stack? Entire computing stack. Perhaps a better word for it is levels of transformation. This is really what happens to a problem that you're trying to solve, and how does that get translated across the entire stack. And I'll show you a picture of the stack. But I'll start with a high-level goal. This is Richard Hamming, who said the purpose of computing is insight, right? In the end, we're all humans. We're looking for some insight to solve a problem. And we're doing computation to get to that insight. That insight may be to discover a drug that cures a disease, right? Or to get to that insight that would lead to that drug. And do you guys know about Richard Hamming? How many of you know? It's OK to say you don't know, by the way. Not knowing is, some of you know. That's good. Do you know what he's famous for? By the way, this looks like him. Apparently, he has a black cat. What codes? Error correction codes. Yes, that's right. Do you know about Hamming distance? Yes? Everybody knows about Hamming distance? No, that's good. Well, I will digress sometimes in this course, because there are some important fundamental concepts, I think, that we should study. Hamming distance is very simple, and it does have implications on error codes. Basically, Hamming distance, and I believe Hamming specified this in error detecting, his seminal paper. I may not get the title fully correct, but error detecting and correcting codes. In 1950, and I believe it was a Bell Labs journal, systems journal. He specified what is called a Hamming distance. Basically, this is a very simple concept. If you have two strings that have the same symbols, if you will, same alphabet, and if you have equal length strings, Hamming distance specifies by how much these two strings differ in the symbols. For example, I'll take my TAs here. They're sitting in the back, and it turns out their names happen to be of the same length. I guess Yungu and Justin. Is that same length? So I can count, which is good. A good start. Hamming distance is in how many locations these two strings differ. So how do you compute this? Y is different from J, 1. O is different from U, 1. O is different from S, 1. N is different from T, 1. Wow, you guys have nothing in common. G is different from I, 1. U is different from N, 1. So the Hamming distance between these two strings is 6. Right. Well, you could do better probably, but OK, I guess I'll take my last name. No, that doesn't work. I'll do Mutlu. Make up something. What is the Hamming distance between Yungu and my name? And you will tell me that it's 5, right? So we have one symbol in common. That's the Hamming distance. Right? So you could apply this to binary also, right? Let's say you have two 4-bit numbers. One number is 0, 0, 0, 0. The other number is 0, 0, 0, 1. The Hamming distance between these two numbers is what? 1, right? So Hamming distance between these two numbers is 1. Or you could be more formal. Hamming distance between 0, 0, 0, 0 and 0, 0, 0, 1 is 1. Because they differ only in one location in their symbols. Why is this interesting? Well, if let's say you have a value that's stored in a memory location, let's say. Normally, if there is no error, the Hamming distance should be 0, right, between itself and the erroneous part of the value. Right? But if there is one error that happens, you have stored 0, 0, 0, 0, and later you read it 0, 0, 0, 1, the Hamming distance is 1 between them. So you can design error-correcting codes that can correct values with different Hamming distances. I'll not go into that in detail. That's the subject of a different course. But that's the concept of the Hamming distance, a way of understanding the magnitude of difference between two strings that have the same length. Make sense? And I'd encourage you to read this paper also. And these papers will be put up online, right, by my TAs. And I'll give you a lot of references, both fundamentals and recent research. And if you would like to dig deeper into the course, into the material, these are very good references to read. And you can see that this is from 1950, right? It's always good to look at all the original sources and understand. Some of these may be hard to read. It's actually very theoretical. It's an information theory paper. But hopefully you'll enjoy it. Actually, while we're on the subject of Hamming, I'd recommend one more thing. Hamming has given an address called You and Your Research. And I know not all of you do research, but I would highly recommend this reading. He gave a talk in Bell Labs after he retired in 1986 and talked about his experiences in doing research and how should a researcher look at research from his point of view. And I think he has a lot of great gems and advice that are generally applicable beyond research in how you look at computing, how you look at actually describing your ideas to others such that you can have more impact in the world. So I would encourage you to read this paper. These are not necessarily required, but this is a beautiful talk. And I think you can find the video of the talk also somewhere, right? So Justin and Yungu will link the video. So I would strongly encourage you to read and look at this material. Because that will be, even if you're not going to do research at some point in time, that will be useful for you in the future. And in fact, another way of looking at life is everything is research, right? Even if you go to a company and implement something, you'll be doing research. OK. After that digression, let's get back to levels of transformation. Let's not ignore Hamming, but get rid of his picture. The purpose of computing is insight. How do we generate insight? Well, we gain and generate insight by solving problems, right? We have a problem at hand, how to cure cancer. And now we ask questions to solve that problem. We need insight to figure out what is cancer affected by, right? How does it come about? What kind of drugs interact? What kind of a drug should we design to get rid of these cancerous cells? To even stop the progression of cancer? Or maybe how do we modify the genetics of a species such that it's perfectly immune to cancer, right? All of these questions. So how do we get there? These are all actually very, very computational problems that people are working on. Well, maybe we can ask the computers to do that. Well, I'm not going to go into that and solve that problem, but that's a tough problem. How do we ensure problems are solved by electrons, right? for a computer, you specify a problem. You have a problem at the very top of the stack. And, well, we're going to design hardware, right? Hardware at the bottom consists of electrons. We can have a problem, and to solve that problem, we can directly talk to the electrons and say, electron, add these two values for me. But that could be a problem, right? Adding two values. Adding a bunch of numbers in an array, let's say. Let's simplify the problem from solving cancer to adding a bunch of numbers. Can you do that? Can you talk to the electrons as a programmer or as a, as a person who wants this problem to be solved? Probably not, right? So that's why we have these levels of transformation. A problem actually gets translated to an algorithm first, because we cannot talk directly to the electrons. It'd be nice if we could say, electrons, do all of this for us. But that doesn't happen, unfortunately. So a problem gets translated to an algorithm, and an algorithm gets implemented or written in a programming language by a programmer. And that later gets translated by the runtime system, or let's take the compiler, into another language, right, which is the language of the machine, the ISA, instruction set architecture, which contains the instructions the machine can execute. And that later gets implemented by what we call the microarchitecture, the design of the logic blocks. And microarchitecture gets implemented by logic gates and wires. And that is in turn implemented by different circuit technologies, right? It could be, for example, CMOS. It could be bipolar logic. Or if it's memory, it could be DRAM, SRAM, different types of logic, different types of circuits. And circuits are implemented by the electrons, right? So these are the levels of transformation. And you've been taking courses across all of the parts of these levels of transformation. What we will cover in this course is mainly these levels. ISA, which is the interface between the hardware and software, instruction set architecture. What is below it? Microarchitecture. And we will define these either later today or in the next lecture. And we will also look at, as I said, whatever we do here affects critically what happens up here. So we'll also look at compilers, how we affect compilers, how the software gets affected, how the runtime system gets affected. Does that make sense? So I lump this as runtime system because there are many components that take a program and translate it into the ISA. And we will see some of those components. Compiler is one of them. But the compiler doesn't necessarily need to be static, right? It could be dynamic while the program is executing. You could dynamically translate a program from a high-level language to the ISA. So keep your mind open. There are many ways of doing things, and this will become a little bit more clear when we talk about the ISA in the next few lectures. Okay? Okay. I guess while we're at it, one question. You guys all know about algorithms, right? Have you taken algorithms courses? Not yet, probably. Well, you know what is an algorithm? Yes? What is it? A recipe, that's good. Yes?
It's a method to solve a problem.
Okay. What are the three characteristics of an algorithm? It's a step-by-step procedure, I'll give you that. And there are three important characteristics. A step-by-step procedure where each step should be effectively computable. That's one. Effective computability is a big characteristic of an algorithm, meaning you should be able to compute it. Right? It cannot be, for example, if you're going from here to, I don't know, to the gym. It cannot be jump over this building. That's not effectively computable for a human, right? At least the way it's specified is not effectively computable, right? You cannot jump over a building unless you're, I don't know, Superman or something. That's the first. The second is it should be definite. It should be precise. So a recipe is precise, right? Each step should be precise. So you cannot hand wave about it. And you can imagine ways of doing that. I'm not going to go into that in detail. And the third thing is the algorithm needs to terminate. Termination is a condition for an algorithm too. It has to end, right? Otherwise, you cannot it's not a procedure anymore, right? Okay? So this is good to know. This is fundamental, even if you haven't taken an algorithms course. Okay. So what does this levels of transformation actually enable? It's really abstraction, right? We're abstracting some things by going up in these hierarchy or levels of transformation. They create abstractions. What is an abstraction? Basically, a higher level in that picture needs to know only about the interface to the lower level, right? Not how the lower level is actually implemented. For example, a high-level language programmer does not really need to know what the ISA is and how the computer actually executes these instructions, right? And they may not even need to know what an instruction is even, right? You write a program in a very high-level language. You just say, you add this to the list, add an element to the list. That has no concept of instruction, really. Right? So at that level, you have this abstraction. And this is nice, right? Because abstraction improves productivity. You don't need to worry about decisions made in the underlying levels. You just say, add this new element. Let's say you're programming a transaction. Add this new value that's deposited into this bank account, right? You don't need to worry about every single instruction to do that. You don't need to worry about where things are stored in computing. So this improves productivity a lot. You don't need to worry about the lower levels. You just need to worry about the interface to the next level underneath. For example, one other example is, I guess, if you program in Java versus programming in C. Java is a higher level language. It improves productivity, right? Its abstraction level is higher. Versus assembly. If you had to do everything in assembly, your productivity would tank, right? Or you could actually program in binary. Have you guys done that in previous courses? Yeah? No? You could actually write the zeros and ones. A little bit in 213, right? Yeah. And was it easy? Maybe it was easy when you learned it, but you don't want to write everything in that, right? Exactly. So you wouldn't be productive if you wrote programs that way. Now imagine even breaking that abstraction. Even zeros and ones are abstractions, right? Because eventually they'll get implemented by control signals at the bottom. They're really controlling ALUs or muxes in the machine. Now imagine programming at that level by specifying control signals of every transistor or every logic gate. Maybe transistors don't necessarily have control signals. They do, actually. But imagine doing it at that level, right? Now that's a terrible abstraction for productivity, right? So abstraction does improve productivity. But you could do programming at all of these levels. And we will see how to program these control signals maybe in lecture 5 or so. So abstraction improves productivity, which is great. But then why take this course, right? Why should anyone take this course? Well, if you want to design the hardware that implements those abstractions, you should take this course. But why should other people care about it? Why would you want to know what goes on underneath or above? Well, as long as everything goes well, not knowing what happens in the underlying level is really not a problem, right? If everything is nice when you write your programs at that high level of abstraction, not knowing how the computer works may not be a problem, right? Unless you're really designing the computer, which many of you want to design the computer, I think. But once problems happen, you really need to know, you really need to break those abstraction layers and understand what's going on. For example, what if the program you're running is slow? How do you understand that? If you do not necessarily know how the machine works, how the machine accesses memory, for example, you may not be able to figure out why your program is slow. What if the program you wrote does not run correctly? Many errors programmers make actually are pointer errors. You guys are programmed in C, right? You probably have made pointer errors once or twice in your life. If you haven't made it, I'd like to give you a prize. Who hasn't made any pointer error in programming in C? And use pointers, of course. If you haven't used pointers, then you will not make an error. Okay, good. I'm not the only one then. And if you do not understand how those pointers are implemented, it's very hard to debug those programs. Now, I'm not saying you won't be able to, but the time to debug those programs increases if you do not understand what a pointer is. A pointer is an address of a memory location, right? And if you do not understand break the level of abstraction and know that concept that you're pointing to memory, if you haven't actually allocated that memory, something bad happens. Or if you haven't initialized that memory, there's something still present in that location. And if you dereference that, you're dereferencing a potentially random address, right? That may be why you're getting a segmentation fault, for example, at the higher level of abstraction. If you don't understand that, you can have much more power in programming systems and debugging your systems. Or what if the program you wrote consumes too much energy? This is even harder, right? How do you know? Today, many of the programmers program these devices. Well, one of these devices, right? And energy is a huge concern in these devices. If the programmer doesn't understand what consumes energy and what does consume energy, maybe they're not writing a good program anymore, right? Maybe energy is the new performance today. And to be able to understand what consumes energy and what doesn't consume energy, maybe you should know what's going on underneath, right? Like how much energy does a memory access cost versus how much energy adding two numbers cost? How much energy does moving data from here to here cost? And they're actually orders of magnitude in difference in some of these things. OK, maybe we'll get to that too. On the other hand, this is the programmer's view again, right? You would like to know what's going on underneath in hardware to be able to solve these problems. If you're the hardware designer, a similar problem happens. Why would you ever want to know what happens upstream, right? What is your impact on the programmer? Because what if the hardware you designed is too hard to program, right? How would you assess that if the only thing you know is your level, the microarchitecture? If the only trade-offs you make is within that level? Basically, how do I optimize this gate? Do I make it bigger or smaller? If that's the only trade-off you make, then you're not considering what happens upstream. So you may be designing a hardware, a multicore processor that's impossible to program, right? Or almost impossible to program. So that's one other reason to break the abstraction layers. And again, similarly, the hardware. What if the hardware you designed is too slow because it doesn't provide the right primitives to the software? It doesn't give the operating system the right hooks to do things fast. And we will see some examples of this. OK? So one goal of this course is actually to enable you to cross the abstraction layers, understand how a processor works underneath the software layer, and design it also, and how decisions that are made in hardware affect the software and the programmer. OK. So I'll give you an example from my own research and my students' research. And this is another fascinating topic. So let's take a look at it. You all know about multicore systems. Everything is multicore today, right? What is a multicore system? And this is an old multicore system by now. This is AMD Barcelona. Is it circa 2007? I guess who is enough of a computer hardware buff to know that? I think it's around 2007 or so. It's a 4-core system. What you have is these cores. These are basically processing engines. And they have some level 2 caches. Level 1 cache is actually part of the core. I'm not showing it here. And we will learn why I consider that as part of the core rather than something separate from the core when we cover the concept of caches. Well, what is caches? You already know from 213, right? It's to enable fast memory access. Instead of going to slow memory all the time, why don't we place some data into fast but small memory close by the processor, such that hopefully most of the accesses hit in these caches, and we don't need to go all the way out to slow memory. And there are many levels of caching on this chip. There's a shared L3 cache across different cores. There's a memory controller that controls the DRAM memory. There's the interface to memory. And there's banks of memory. So in this course, we're actually going to cover the entire thing. We're going to cover how each of these different components work. And hopefully, that should be fun. But I'll give you some detail here. So let's take a look at what happens to two programs when we run them on this chip. Imagine only a 2-core version of this chip for now. So this is a study that we did. You have two programs, MATLAB and GCC, and you run them together on this 2-core chip, and we measured the slowdown each program experienced compared to when it's run alone on the same chip. So instead of using 2 cores, you use only 1 core to run MATLAB. And when it's run with GCC together on 2 cores, MATLAB slows down by 7%. So when you're running GCC next to it, MATLAB doesn't get affected that much, right? Which is probably good for MATLAB. But GCC gets affected terribly. It slows down by 3x, 3.04 times, compared to when it's run alone on the same system. Now this is not good, right? This is a pretty bad slowdown. When you're running 2 programs on a 2-core chip, you get a 3x slowdown. And I'm not showing it here, but this slowdown is actually very unpredictable. GCC slowdown changes significantly depending on what other program is running next to it. So this problem is not solved if you go to the operating system and say, oh, I'm not going to give high priority to GCC. What if you care about GCC a lot, right? That's the program that you want to run fast. You don't care about MATLAB that much, but you do want to run it. And by the way, change this MATLAB to a virus checker, if you will. You do want to run your virus checker once in a while, right? But you don't care about it as much as you do care about whatever interactive program that you're using. So if you go to the operating system and nice MATLAB, if you will, you know how to do nice, right, in Linux? Yes? No? So nice is a command in Linux that changes the priority of a process so that it doesn't get scheduled as often. And I encourage you to understand how that gets implemented in the operating system level. That's not the subject of this course, but you could do that. You could assign low priority. You could actually do this in Windows to different operating systems that have different interfaces to reduce the priority of different processes. But if you do that in the operating system, well, you get the same slowdowns, actually. Nothing changes. Why? Because now you have the operating system sees 2 cores, and the 2 cores get scheduled with these 2 programs, and it doesn't take away the cores from these programs. So these keep executing. So nothing changes. So we call this the memory performance hog. And this is a bad thing because we have no control in the system to make GCC run fast. Well, I guess we do have control. We can say, don't run MATLAB, right? But what if you do want to run MATLAB? Then you're if you don't run MATLAB, you're underutilizing your system. And the whole purpose, one of the purposes of a multi-core system is to be able to get high performance by having high parallelism. Why build a multi-core chip if your goal is to run only 1 core? Right? Makes no sense. OK, so I guess this is one example of why someone should break down these abstraction layers and understand what's going on underneath. Can you figure out why there's a disparity in slowdowns if you do not know how the processor executes the programs? If you have no clue how the system is designed, can you figure this out? I would posit no, and many of you are shaking your heads, which is right. Well, you would like to figure this out, and can you fix the problem without knowing what's happening underneath? And the answer to that should be no. If the answer to this is no, this is probably no also. And the key is efficiently, of course. You can always fix the problem by running only 1 application in a 1,000-core system. OK. So let's take a look at why this happens. I'd like to go a little bit deeper into why this happens and give you an understanding of how the system works. And we'll cover this in more detail when we get to the memory interfaces, but learn this now. So why do you get disparity in slowdowns? This is the system. This is what the system is like, core 1, core 2. You have these caches, interconnect, memory controller, and memory banks. This part is shared between the 2 cores. And we're running MATLAB and GCC, 2 applications. And what ends up happening is MATLAB and GCC both miss in their caches. And MATLAB misses a lot more. It sends a lot of requests to the memory controller that gets queued up. And by the way, the latencies are very high here. It takes hundreds of processor cycles to access any of these DRAM banks. And it turns out this memory controller, whose job is to schedule requests, arbitrate between the requests of these different applications. And it turns out it prioritizes this MATLAB application over and over. So there's unfairness in this memory controller. And that's the reason why this is happening. You have an unfair hardware that leads to very large disparity in slowdowns. Now this is good. Now we've gone below one level of abstraction, right? Now we understand why this is happening. Of course, you need to eliminate other causes, other potential causes of why this is happening, and I'll let you think about what could those causes be. So in this system, if the L2 cache was shared, L2 cache could be another reason, right? Because one program can be evicting the blocks of another program. And we will get to that when we cover caches. If you don't understand what I said just now, ignore it, but we'll get to that. Okay, so next level, you could say, why is this happening? Why is this designed to be unfair? Right? Well, there's a reason for it too, in fact. Now let's break another level of abstraction and understand how this DRAM bank itself is designed. It turns out, well, DRAM bank stores data, right? And it consists of two-dimensional array of cells, columns and rows. And each thing over here, each box, stores a bit, a 1 or 0. And you can address a column and a row. To read data out of this chip, you need to read an entire row into what is called a row buffer. And initially, that row buffer is empty. And let's say the processor wants to access an address at row 0, column 0, which is this little thing. The memory controller first needs to activate that row, send this row address, which gets decoded, and the row gets activated. And the DRAM chip places that row into this row buffer. And the memory controller then needs to send the column address to the DRAM bank. And that column address is sent to the bank, and the appropriate data at that column address gets muxed out of the row buffer. You guys all know about muxing, right? I'm not showing you all the detail here, but you get the appropriate data that way. And the data gets sent to the processor, to the memory controller back. Now let's say the processor now wants to access row 0, column 1. Now this row is already in this row buffer. And this is called a row buffer hit. You can think of this as a small cache of a row. Right? Now the memory controller doesn't need to activate the row again, because the row is already here. It already took the time to bring the row there. The memory controller can just send the column address, and the DRAM chip can mux out the data and send it back. If the next access is to column 85 within the same row, again, this is a row buffer hit. And the memory controller only needs to send the column address, and the data gets muxed out and sent back to the controller. So now you're seeing that these row buffer hits are fast, right? Which is nice. Let's say the processor needs to access row 1 now and column 0. Well, row 0 is in the row buffer, so the memory controller cannot just send the column address. So now what it needs to do is it needs to close this row. This is called a row buffer conflict, by the way. The memory controller is accessing a row that's different from the row that's already open in the row buffer. The controller needs to now close this row, and we will see what this is later on when we cover DRAM exactly. It needs to send the new row address to activate row 1, the chip places row 1 into the row buffer, which takes time. Then the memory controller needs to send column 0, column address, and the chip muxes out the right data and sends it to the memory controller. Now this row buffer conflict took a whole lot longer than a row buffer hit, right? You need to close the row, open the new row, and mux out the data from the appropriate call. So a row buffer conflict is much more costly than a row hit access. In fact, it takes 2 to 3 times longer than a row hit access in today's chips. And current controllers take advantage of the row buffer. They're designed to minimize these row buffer conflicts. So there's a commonly used scheduling policy, which we will cover in more detail later. It is a horrible acronym. Ignore that for now. It's first ready, first come, first serve. But I'll call it row hit first policy. Basically, among all the requests in the queue that are queued up in the memory controller, first pick the request that hits in the row buffer. Schedule that first. And if there's no such request, or if there are multiple such requests, How do you arbitrate between them? Well, pick the older request among those first. So it's a prioritization level, right? Row hit first, and then oldest first. And the goal of the scheduling policy is reasonable, right? It tries to minimize the row buffer conflicts or maximize the throughput. Throughput is how many requests do you service per a given unit of time out of DRAM. And if your latency is low to service a request, which is what a row hit is, your throughput is also increased if you service that. Okay, the goal is to maximize DRAM throughput. But when you have multiple threads, like we had in MATLAB and GCC, these share the DRAM controller. And the DRAM controller is trying to maximize DRAM throughput by prioritizing row hit requests. This policy can be very unfair, right? What if MATLAB has high row buffer locality? Meaning it always keeps hitting in the row buffer. And GCC doesn't. Well, now we have a problem, right? The memory controller will always prioritize MATLAB, right? Until MATLAB stops hitting in the row buffer. And that is one of the problems in this case. This row hit first unfairly prioritized threads that keep hitting in the row buffer, threads that keep on accessing the same row. This other prioritization level is also unfair. Oldest first policy. Why is that unfair? Let's assume that the row buffer doesn't exist for a while. The policy is pick the oldest request in the queue. Yes.
Well, memory bursting. So like if MATLAB bursts like 10 requests in a row, and then comes in the GCC request, then you have to wait for all the 10 to go away before processing the other one.
Exactly. Yes. If MATLAB, I'll say it in a different way. It's bursting. If MATLAB is very intensive in terms of its memory accesses, and GCC is not that intensive, MATLAB generates 10 requests or 100 requests for GCC's every one request. Now GCC needs to wait until all those 100 requests go away. Or maybe because those appear to be older, right, to the memory controller. And that's an unfair policy when you have multiple different streams that are trying to access memory. So it turns out DRAM controller is vulnerable to denial of service attacks because of this. So you could imagine MATLAB denying service to GCC, right? And you can easily write a program like MATLAB. I'll show you right now in today's system. People are fixing these problems right now, but I'll show you how do you write this. Well, this is it. I'll call this stream. And this is one of your readings for this week. So you'll learn more about this as you read this paper. But it's a simple program. Basically, you initialize two large arrays, A and B. And what we do in this program is we copy array B into array A, element by element. And we ensure that each access is a cache miss. Well, how do you do that? Basically, elements are huge, right? You could do, that's one way of doing it. Or the distance between elements is huge. That's what this index ensures. You're basically streaming through memory. So you get very sequential memory access, which leads to very high row buffer locality. Because we're assuming that a row consists of consecutive memory addresses. And this program has very high row buffer locality. And when you measure it, it's about 96% hit rate in the row buffer. And it's very memory intensive, right? Every access is a cache miss. Now let's take a look at another program that's not exact like MATLAB and GCC, because GCC actually is not very memory intensive. But let's take a look at the same program, except it accesses memory randomly. You're copying array B into array A, element by element, except you're not going through elements sequentially, but you're going through randomly each array. You're taking a random location in B, copying it to the same random index in A, and picking another random location and copying it into the same random index in A. Now you don't have very good row buffer locality, right? Because you're not streaming through the row buffer. In fact, this has 3%, surprisingly 3% hit rate in the row buffer. And this is similarly memory intensive because if you are accessing your arrays randomly, the likelihood of getting a cache hit within that array is low, right? Within that access pattern. And we will see all of the operations of caches during this course. So if you didn't understand my last sentence again, wait. OK, so you have these two applications. Now what happens when these two applications are actually run together on the system? This is our bank. We have a row buffer, and as I told you before, and this is a request buffer going to that bank. And let's say these blue requests are from stream, the red requests are from this random access application. And let's say initially this row 0 is open. It doesn't matter. Eventually it will get open. But the memory controller, what it does is basically it prioritizes these row hitting requests. And the streaming application's requests keep on hitting in the row buffer, right? Random application generates requests, but its requests don't get serviced because the streaming application keeps generating requests to the same row buffer, and they get prioritized over and over and over. So that's why this random application starves. Well, you can do the calculation now, right? Yes?
Why would the random application generate 3? Wouldn't it block on the first request?
Oh, okay. Now you're thinking. That's good. I like that. We will see this later in the course, but if you have a simple pipeline, what you said is true. If you don't buffer any further instructions into the future, if you don't look ahead in the instruction stream, you get a load, you send it to the memory, you miss in the cache, and the processor blocks. That's called in-order execution. But if you have a machine that does out-of-order execution, what happens is the processor has enough buffering to look ahead in the instruction stream and the ability to find independent instructions and execute them while it's blocking on another instruction. So you could generate multiple requests at the same time in an out-of-order execution engine. And we will see how that's done in this course, how you actually design an out-of-order execution processor and how you can generate multiple requests. Well, that's good. So you probably haven't seen out-of-order execution so far, right, in any of the courses?
I don't know if we could run the whole RAM.
So that's another good way of thinking.
I'd be impressed.
Yes, that's another good way of thinking. You don't, it turns out when we do this study, you need to pre-compute all of those random values. So you don't, that rand function is an abstraction that I showed over there. But when you actually, if you actually need to do this experiment, what you really need to do is not put the rand function over there, but pre-compute all of those indices randomly and do another access to that index. But good. Okay, I'd be happy to talk to you about more on this, or Junger can talk to you too, Junger and Justin. Okay, yes, so you can do the calculation with a row size of 8 kilobytes and a cache block size of this. 128 requests of this streaming applications are serviced before a single request of the random application. And that's the cause of the denial of service or degradation of service. Okay, now you know what happens underneath, right? So how do you solve the problem? Well, I guess one question is, what is the right place to solve the problem? We have all these options, right? Where can you solve the problem? Can the programmer solve this problem? It's not clear, probably not, right? Because the programmer may have no control over which applications are run in the system together with their own application. In fact, today, you send an application to the cloud, right? Cloud meaning maybe you're executing your simulation in Amazon's compute services. You have no idea what other applications are running on the same machine with your application. So how can you have any control over this problem? Right? Even in your own machine, you usually cannot control what is running with your own application. System software, can it solve the problem? Maybe, right? And I'd like you to think about it. I'm not going to give you answers to these. It's hard for the system software to solve this problem also, and the paper you will read will make some cases as to why it's hard to do that. Compiler, can you solve this problem in the compiler? Well, actually you could, but it would be terrible, right? I mean, the compiler, you could randomize every single access, right? That may not be that hard, actually. So that no application ever has any locality. That's easy. That's a much easier problem to solve than making applications that have locality, right? Or exploiting locality. In fact, people have been designing compilers to improve locality for decades. And that's a tough problem. But the other part is very easy. Randomize everything. But that's not the solution you want, probably, right? That gives you terrible efficiency in the system. Hardware, memory controller. Can the memory controller solve this problem? Well, probably yes, right? Instead of doing unfair scheduling, maybe you have a much fairer scheduler. And the paper you will read has a solution to this. It's not the best solution, but it's a solution. Or maybe we should think differently, right? Maybe we should design DRAMs such that this row buffer is not a problem. Can you solve this problem in DRAM? Right? Maybe not in its entirety, but maybe you can design a chip, DRAM chip, that is not as amenable to these kind of denial of service attacks. Right? I'd like you to think about it. Circuits, I don't know. I haven't put much thought into that. But we will look at solutions at this layer in this course. So I guess one other reason I wanted to cover this is there are two other goals of this course which are critical, I think, which should probably be the goals of every course that you take here. And they're implicit goals of every take that you take at CMU, hopefully. Make you think critically. So there could be solutions across the entire stack. And hopefully in this course, you'll understand how to think critically about each solution. There are always advantages and disadvantages to every single solution. I've yet to see a solution that has no disadvantage. I guess there are some solutions that have no advantage, like the one, I said, where the compiler randomizes every access. But you could argue that that may have an advantage also in terms of security, right? Maybe no one can figure out what addresses that a program accesses, and that could be useful in a security context. Well, I guess this goes back to the next one. The other goal is to make you think broadly. Broadly meaning, even though there may not be a seeming advantage or disadvantage for a particular solution, if you think broad enough, maybe there is an advantage. Like if you think different aspects, security, for example, maybe there's an advantage to a solution, right? So hopefully, in this course, we will try to cover a lot of problems, solutions, and trade-offs such that you can think critically and think broadly. And this is true for everything you see and everything you read also. You'll read a lot of papers. You'll read a lot of slides also. But think critically. And I'd like you to ask questions also. OK, so recap some goals of 447. We'd like you to teach, enable, and empower you to understand how a processor works, implement a simple processor with not so simple parts. Some of the things that you will implement will not be that simple. So we'll cover cache coherence, for example. One of the labs you will design, you will implement the MESI cache coherence protocol, last lab, lab 7. That's not necessarily very simple, but hopefully you'll learn a lot from it. You'll hopefully understand how decisions made in hardware affect the software programmer as well as the designer. Think critically and think broadly across the levels of transformation. And understand how to analyze and make trade-offs in the design. Like most engineering fields, and I think this is particularly true for computer architecture, the trade-offs you make are critical. OK, maybe I'll take a break after this, but I'll give you an overview of the course with that prelude. What I would like to cover, now we can start the lecture, initial part of the course. Wow. We'll cover course logistics, information, and requirements. I'll tell you what 447 is about, and we'll look into some lab assignments, homeworks, readings. And I'll assign you homeworks, and I'll be assigning you a lot of homeworks on labs, so hopefully you'll be OK with that. And homework 0 will be, you all picked up your homework 0, right? OK, that's an easy one. I don't think we'll get to basic concepts in computer architecture, but we've already covered some things. So make sure you get a copy of homework 0 and your syllabus. I do not want to print out the syllabus. It's online. You can get that information. Who are we? I guess, I don't know if this looks like me anymore, but that's me. My offices, actually I have 2 offices right now, but I'll tell you which one. I'll hold my office hours here in A305. But you may be able to find me at CIC 4105 also. And office hours will be Wednesdays 2:30 to 3:30 p.m. after the lecture. And you can find other information about me on the website. I got my PhD from UT Austin in 2006. After that, I worked at Microsoft Research before joining Carnegie Mellon. I did a lot of hardware, software research at Microsoft. And I have experience at Intel and AMD during graduate school and afterwards working with them. And if you have any questions about any of the industry, I'd be happy to talk with you. If you're considering job options, for example, or internship options, I'd be happy to talk with you about those things. So feel free to use the office hours or other times to talk with me. I like researching and teaching many topics. You can see that on my website too. But I work on computer architecture, hardware, software interaction, many core systems. We do a lot of work on memory, and we'll cover actually a lot of these topics in this course to varying detail. This is a very fundamental course. Well, I don't think I'll cover all of these for you, but hardware security is interesting also. So what we've talked about is an example of security issues caused by hardware design, right? Okay, so that's me. We have other people as our teaching assistants. Yungu is sitting in that corner, and he's awake. That's good. He's my PhD student, and he's actually worked on some of the solutions to that problem that I just told you about. Better solutions than we had designed earlier when I was looking at the problem. So you can talk with him about his research, and he'll be, you'll get to interact with him regardless if you talk to him about his research. And this is his office hours. He tends to be up late, so you can find him at CIC probably late. Justin, well, he's over there too, in the back. And Justin is also my PhD student, and he's doing a lot of research on computer architecture again, a lot of these topics, memory, and new technologies. So he can talk to you about his research, and he'll be your TA. And I guess he has lunchtime office hours. We're going to try to distribute the office hours so that you can find any of us. And also by appointment, by the way. I didn't put by appointment here, because otherwise that would cover the pictures. And we do have Andrew Carnegie also, who's going to be your TA. You wish, or you don't wish maybe, I don't know. I don't know what you think about Andrew Carnegie. He was a great philanthropist, but I don't know if you would like to work for him as one of his workers, industrial workers. Probably not, given that you're pursuing an engineering degree. Well, this is not Andrew Carnegie. This was supposed to be Jason's picture, but he sent me his picture in the like 15 minutes before this lecture, so I was able to get it in. They look similar, right? Maybe, yeah. Yeah, Jason is another TA. He's not here right now. I think he's coming back from China, right? Maybe tomorrow or Wednesday. And he has taken this course last semester, so he'll be able to help you a lot with the assignments, like all my TAs. And his office hours are to be determined. So now that I've introduced everyone, it's your turn to introduce yourself to us. And that's the purpose of homework assignment. Homework 0, who are you? And this is your opportunity to tell us about yourself. And I'd like you to take the time to actually fill it in nicely. There are a lot of questions. There's not enough space, probably. You could use multiple sheets. You could use the back of the sheet. It's due January 23rd before class. And by the way, next Monday is the MLK Day, Martin Luther King Jr. Day. So there's no class that day. So you're not going to turn in at that time. But I'd like a hard copy of this, because I read every one of these sheets carefully. And this is the way of getting to know you, initially at least. And attach your picture. That's very important too, because I could read a sheet and not know who you are, right? Without knowing what you look like. And all grading is predicated on the receipt of homework 0. You guys know about predication, predicates? At some level. We'll cover that also. Instructions can be predicated also, right? Are you guys aware of that? There's an instruction set architecture called the ARM instruction set architecture, where every instruction has a bit associated with it saying whether this instruction should actually be executed by the processor or whether it should be ignored by the processor. That's called a predicate bit. ARM calls it conditional execution. But it's really, the concept is predicated execution. Well, let me see. It's called predicated execution, and we'll cover it in a little bit more detail, I think. Wow. I guess that has been sitting there for a while. It's breaking when you touch it. Predicated execution. Yeah, the idea is basically the execution of an instruction is predicated. And this is an alternative to control flow, right? For example, if x is equal to 0, a is equal to 1, else a is equal to 0, right? One way of implementing this is using branches, right? You could have an instruction that compares x, let's say x is in register 1, to 0, or there are a lot of instructions that architectures that do this. Compare equal to if equal to 0, R1, and set the result in R2, or set the result in a condition code. And then you can say branch 0, branch if 0, to, I guess if it's equal to 0, then you would like to do a equals 1, right? Then you move 1 into a. Maybe I will use x here. And the else condition is, in this case, a is equal to 0. Move 0 into a, and then you need to do an unconditional branch to get out of this, right? I've gone through this relatively fast, but you could translate this code into some assembly code like this, right? Or pseudocode. Predicated execution gets rid of all this, or most of this, right? Here, now you need to do a lot of branches. The downside, well, you'll see the control flow problem soon. The processor, if you're designing a pipeline processor, you're executing multiple instructions in different stages. And when you get to a branch in the fetch stage, you need to know what instruction comes next after that branch, right? To move the branch to the decode stage. Let's say there's an execute stage in the pipeline. But you cannot move it because you do not know what instruction to fetch until that branch is executed. The goal is to fetch that branch, decode it, and execute. And these happen in different clock cycles, different stages. When you fetch the branch, you don't know what's the next instruction. It could be this. It could be the target of the branch. Well, you need to guess. And existing processors actually guess. That's one solution to the problem. Or you could stall. If you stall, then you have a problem, right? You're not utilizing your pipeline well. And you will see this in a lot more detail. You'll be intimately familiar with it. You'll actually implement branch predictors as part of your assignment. How to figure out what direction the branch goes. What is the next instruction? So one other way of solving the problem other than branch prediction or stalling is to use predicated execution. And the idea here is each instruction is a bit associated with it. And that bit is set by a predicate setting instruction. Let's say, so this is the branch code. And I'll write the predicated code for this, which is a little bit simple. In this case, we still need to figure out whether this thingy, whether x is equal to 0, right? Compare equal to 0, x, and set the predicate bit. Predicate bit is set to, I guess I'll set to 0. I guess P1 is set to 0 if x is equal to 0. Well, P1 is set to 1, let's say. You could define it that way, if x is equal to 0, saying that predicate is true, right? And you have now an instruction. The next two instructions can be predicated on that predicate value. If P1, then move A1 into A. If P1 is not true, if P1 is true, then move 1 into A. If P1 is not true, then move 0 into A. That's the predicated version of this code. No branches. Branches are gone, right? We've changed the instruction set architecture. Now, when the machine executes this instruction, it checks if P1 is true. If P1 is true, then this instruction is executed. It takes effect. If P1 is false, this instruction is treated as a no-op, no operation. It doesn't get executed. Similarly for this instruction. If P1 is false, this instruction gets executed because the predicate becomes true, right? If P1 is true, this instruction is a no-op, right? So now you have much denser code, 3 instructions to do the same work as 1, 2, 3, 4, 5 instructions. That's one advantage here. The second advantage is now you don't need to predict branches, right? Now you don't have the problem in a pipeline processor when you fetch a branch. You don't have to decide what is the next instruction because you know what is the next instruction. It's sequential code now. There is no branch. You fetch all of the instructions, and at some point, predicate becomes available, and you execute or not execute. So this is an example. Well, I don't know how we got to predicated execution, but yes, all gradient is predicated on homework 0, right? But this is, you see these concepts in real life also. But basically, this is a trade-off. This sometimes is a good idea, sometimes it's a better idea. And I'll let you think about when it's a better idea. Actually, when is this a better idea? Yes?
Depends on the length of each branch. If the branch is long.
OK, yes, exactly. Exactly. I gave you a nice example for this predicated execution, right? Because there's only one instruction that's predicated here. But imagine there are hundreds of instructions. If x is 0, you have hundreds of instructions. Well, is this a good idea then? Probably not, right? Or it depends on that. It depends on something else. What if you have a great branch predictor? It predicts 100% accurately, right? In that case, this is not a good idea because you're always executing something you're not supposed to execute, right? Whereas if your branch predictor was 100% accurate, you're always jumping to the right place and fetching the right instruction, right? So if you have that, then you don't want to do this at all because you're always wasting energy, wasting your pipeline slots in this case. So it's a trade-off, right? And this is actually a very complicated trade-off, it turns out. It's very hard for the compiler to make that trade-off. There are ISAs that have both instructions. Well, ARM is like that, actually, but Intel IA64 is a predicated machine. And people who have designed the compiler for Intel IA64, you guys normally don't use IA64, right? Not many people do. But they've done a lot of studies. They've designed a lot of heuristics in compiler to figure out whether this is better and this is better. And they found with the best heuristics, they can improve performance by 1.3%, I believe, compared to a very good branch predictor. So it's tough. It's not very easy to make that trade-off. But there are people who would actually pay for that 1.3% performance. It's additional performance. It does enable their applications to go much faster. OK, so that's one example. I guess if we have to do this, our predicate will be, I guess, homework received. Right? We'll set the predicate. If this is true, I guess what will your grade be then, right? Let's see. If the predicate is true, your grade is, well, let's do this. Is a computed grade, which I will get to, hopefully. And if the predicate is false, your grade is 0. Right? That's the algorithm for this. Homework 0. Another way, turning your homework 0. OK. OK, where do you get? I think, should we take a break or should we just go through it and end early? End early. Is that the consensus? How many people say end early? That looks like the consensus. Who is the dissenter? Don't be afraid to be dissenters. Dissent is OK. OK, so end early. I'll go fast. So you know the website. I'm not going to go into that, but we will have a lot of information on the website. And you can see that from last year's website also. I will not take off last year's website. You can see what kind of schedule we could perhaps follow by looking at that website. We'll have lecture notes, project information, homeworks, course schedule, handouts, papers, and videos also. We have 2 different kinds of videos. I don't know which one will be posted in the end, but we'll figure out how to do these on the website. Blackboard, which is not a great piece of software, by the way, will be used for you to upload your homeworks. That's how we will collect homeworks, because that's the only software that I know of at this point to do that. Except for homework 0. That's supposed to be hard copy. Your email is another source of information, and me and the TAs. If you have any questions, please email all of us. Don't email only one person. The response time will be much shorter if you email all of the TAs, and me also. Okay. Probably the response time of the TAs will be much faster than my response time, but depends on the subject also, yes?
And there's a specific mailing list for emailing all of the instructors of the course that's on the list.
Okay. Do you know what that is?
It's 447 instructors.
Okay. So you got that, right? It's 447 instructors. Now you can find all of this information on the website at ECE. Yeah, something like this. Okay? So you don't need to go and type all of our names. Okay. Lecture and lab locations times. Lecture is Monday, Wednesday, Friday, 12:30 to 2:20. And it's here. Attendance, I will not enforce any attendance, but it's for your benefit, I believe, to learn. I think you learn a lot more. At least I learn a lot more when I interact with the instructor. So I'll leave it up to you, but I'd strongly encourage you to attend these lectures and ask questions while you're attending the lectures. And some days we will have recitation sessions. So this is, the schedule will be dynamic, meaning it'll be determined based on how we go in the course, and it'll be determined based on partially your interests also. But my intent is to lecture 2 days a week on average. It's a gross average across the entire semester. On average, 2 days per week, and have the other day as a recitation session led by my TAs. But this doesn't mean that, so this week, for example, I intend to lecture every 3 days. But some other weeks we'll have recitation sessions for 2 days. And some other days we may actually cancel some of the lectures if we're actually doing well on schedule. Make sense? Okay. Labs, you've already signed up for labs, so I'm not going to go into this in detail. Is this true, actually? This is from the old deck of slides, I think. I don't believe this is true. Don't go there for the labs. This needs to be corrected. I think there's an office there now. Okay. Again, attendance in labs is not required except for checkoff. You need to check off with the TAs for the labs. And you can attend any lab session to ask questions or check off, even though you may have signed up for another lab session. Okay, tentative course schedule. This is in your syllabus. To get an idea of topics, you can look at last year's schedule. You can treat that as a potential prediction mechanism for this year. But that's not the course is dynamic, right? Don't believe that's static schedule. That'll give you an idea of what are the topics. You can even go and study the lecture notes. I'm going to use some of the same lecture notes, so they will be available to you. You could potentially study everything in the course, or maybe you've done it already. But don't believe the static schedule. And I'll not digress too much on this. We'll do that later when we cover runtime versus compile time. But systems that perform best are usually dynamically scheduled. Because you don't, what does dynamic mean? Dynamic means at runtime, right? You don't form the schedule before the lecture happens, before the semester happens. You have a tentative schedule, but you modify it based on what happens during the lecture or during the runtime. So we'll cover compile time versus runtime. In systems, when you design a processor usually performs best if the instructions are scheduled dynamically. Meaning at runtime, you modify which instruction gets scheduled first or next. Another alternative to this is obey the schedule that the compiler gave to you. Compiler gives to you a list of instructions, right, in a sequential order. Obey that schedule, execute instructions sequentially. In that case, if you get to an instruction that takes long, you stall, right, as you pointed out. You cannot go further. Whereas if you do runtime scheduling, you can execute instructions out of order, out of the order that was specified by the compiler. And that performs much better, as we will see. Okay? And that's exactly the reason why we're going to do runtime scheduling, because I cannot predict all the events that will happen in the entire 15 weeks of this course, right? Okay. So what you will learn, computer architecture. What is computer architecture? It's the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets many different requirements: functional, performance, energy, cost, and other goals, reliability, and we'll see that. The traditional definition is actually, it's really what the software designer needs to know about the hardware interface. It's really ISA. The traditional definition of an architecture is instruction set architecture, but it will be more broad, and we will get to this again. This is Amdahl's definition. You all know about Amdahl's law, right? And that's Amdahl. Well, I guess this is Amdahl, but I mean, he's a famous computer architect. And what he said in IBM Journal of Research and Development in 1964 is, architecture is used to describe the attributes of a system as seen by the programmer, i.e. the conceptual structure and functional behavior as distinct from the organization of the data flow and controls, the logic design, and the physical implementation. So it's really what the programmer needs to know about the hardware, which is the interface. What is below implementation is the microarchitecture. That's the traditional definition. But we will cover everything. We will not be sticking to the traditional definition. So computer architecture in the levels of transformation, what we will cover is here. So Amdahl said this is architecture, which is a traditional definition, but our look into computer architecture will be broader. But never forget the traditional definition. We'll get to that again. So this is one of the readings that I'll assign to you for Wednesday or Friday. We don't necessarily have deadlines for this, but this reading will talk about the levels of transformation and how computer architecture has evolved. It's a nice 8-page paper by E.L. Pat. So hopefully you'll enjoy that also. So I'll assign you 2 papers. Levels of transformation, I guess I'll revisit them a little bit. Broaden a little bit. Levels of transformation actually should include something else, which is very, very important to computing, right? Which is the user. Traditionally, you don't see this, but I'd like to think of it this way also, because in the end, we're designing computers for users, different users. A user could be the programmer. User could actually be the user, like me as a user of this. I don't program these. Maybe you guys program this, but my user is actually using this actually. So I'm the user, but the programmer could be the user also. So think about the trade-offs that are made in terms of from the viewpoint of the user also. So I like looking at this levels of transformation with user included. So the entire stack perhaps should be optimized for the user as well, right? The common user. And we'll get to that also. So what will you learn? There are 2 things: fundamental principles and trade-offs in designing the hardware-software interface and the major components of a modern programmable microprocessor. Our focus will be programmable microprocessors. Computing is much broader than just programmable microprocessors, right? It could be very fixed function also. We'll talk about some of those things also, but our main focus is a programmable processor. And how to design, implement, and evaluate a functional modern processor. And focus will be on state of the art, what we have today, and some recent research and trends. This is a very dynamic field today. And you will see this in the next lecture. A lot of things are changing in computer architecture, especially with multicore and issues that we run into in scaling the system further. So you can actually make a big difference in this field if you really understand what is the state of the art and what are the trends. And of course, trade-offs and how to make them, you will learn that hopefully. And how to, in this part, how to design, implement, and evaluate a functional modern processor, we'll have semester-long lab assignments. And these will be a combination of RTL implementation in Verilog and higher level simulation. You will do simulation at the C level as well. So hopefully this will give you both ways. Yes?
Will the Verilog we be using be the system Verilog standard or something older?
I think it's going to be something older. Is that right? Yes. Unfortunately, it's going to be something older because we don't necessarily want to change the entire infrastructure. But that was one of my goals, but that didn't happen. But something older, you guys should be flexible enough to use something older also. OK. So focus will be on functionality and some focus on how to do even better. So your lab assignments will actually encourage you to do even better designs. Like you'll get extra credit, for example, if you design a better branch predictor in your lab assignment. And I'll give prizes. Last year, some people won prizes. Like Jason, who's going to be TAing the course, won several prizes. I think he did a better branch predictor. You may want to ask him. And if your designs are optimized, you'll get extra credit also. Even if you get an extra credit, you'll get a pat in the back. Or it's fun, optimizing your designs. And as I said before, how to decode information will be partly what you will learn. Think critically and broadly. And I guess this one also. How to work even harder. So I'm not going to promise you that this will be an easy course. This will be a tough course, but hopefully you'll learn a lot. So one of the comments that I received from the evaluation last year, which made me very happy, was, this was the hardest course I've ever taken at CMU, but it was the best one. I learned a lot. So hopefully your experience will be the same. Or maybe even better if your experience was, well, I guess you don't want it to be easiest. You want the course to be at a level of hardness that challenges you. So hopefully your experience will be similar. Maybe not the hardest course, but. Okay, goals. I think I've covered a lot of these, but we'll be covering processor, memory, and platform architectures and their fundamental operation principles and design trade-offs. And the second is, hopefully you'll get the necessary background and experience to design, implement, and evaluate a modern processor. And again, it's hands-on RTL and C-level implementation. I think both are very, very important. When you're a computer architect, you really need to know at both levels. Because RTL level design is closer to implementation. C-level design is closer to exploration. And if you try to do exploration, like how to put components together at the RTL level, then you'll have a tough time. Because it's much slower. But if you do exploration, how do I design my cache? How big should it be? At the C level, at a higher abstraction layer, it's much faster, and you can get to a design much faster. Eventually, you'll need to implement an RTL, of course, right? And eventually, it needs to be implemented in hardware. So that's why we have both. Okay, I think I've given you this also. This course is classified under computer hardware, but you will be much more capable if you master both hardware and software and the interface between them. You can develop better software if you understand the underlying hardware, and I think I've given you an example of that. And you can design better hardware if you understand what the software will execute. And if you can design a better computing system if you understand both. And we cover the hardware-software interface and the microarchitecture. So required background, hopefully you all taken 240 and 213. What do I expect from you? Learn the material thoroughly, which means doing everything that's required for it. Do the work and work hard. Ask questions, which you've been doing, which is great so far. Take notes and participate. Taking notes, I've seen many of you doing that also. That's good, because I give you a lot of information that's really not on the slide necessarily. Perform the assigned readings, and there will be some readings that are not assigned, like Hamming's readings, and I again encourage you to do those. That'll give you a much broader perspective. I know this is not the only course you're taking, but it's good to look at some of those things. Come to class on time. Even if you're not on time, come to class. I think that's good. And start early. This is probably the biggest, most important advice that I'll give you. Do not procrastinate. The course will be very, very fast moving. There will be 7, well, I guess that's the next slide. I'll get to that. Don't procrastinate. Start everything early. If you want feedback, come to office hours. Because it'll be a fast-moving course, I cannot give you feedback for every single assignment. So if you want feedback, please do come to office hours. Seek feedback. I'll treat you as adults, meaning I'm hoping that you will know when you need feedback and come to me, and not necessarily me doing the other way around. So hopefully, and I'm open to giving you feedback on anything. Feel free to come anytime. And I guess this is another quote I like talking about. Chance actually favors a prepared mind. So if you're not prepared by doing this, you will not have luck in this course also. And this is true in research also. I think this is a quote by Louis Pasteur. You know about Pasteur? You all studied, right? Pasteurization, how you can actually make milk and wine that doesn't kill people. That's what pasteurization is, right? And this looks like him. So you can all be like him if you actually get prepared and do great things into the future. Okay, this is, again, to emphasize, this is very important. You'll have 7 labs and 7 homework assignments. It'll be heavy. But hopefully you'll learn a lot of fascinating topics and understand how a microprocessor actually works and how to make it work better. So what are those assignments lead to? Hopefully you're not necessarily here for grades. Don't be too focused on grades. I'd encourage you to focus more on learning everything. But grades are, I guess, an unfortunate aspect of being part of the university. There are a lot of fortunate aspects to it too. This is not to be negative. But you'll be evaluated with like this. There's 6 homeworks that are worth 10%. This is mainly for your benefit. It's not worth a lot. You should still do them. And this is mainly for you to learn the material, prepare for everything else. 7 lab assignments, 35%. Midterm 1, 2, 15%. Final, 25%. And there's also our evaluation of your performance, which is 5%, which includes participation and doing the readings and talking about them. And it also will take into account how you progress along the course. This will give us a way of elevating your grade if you're actually doing much better later in the course. Let's say you didn't do well in midterm 1, you got 0% somehow, but you did 25% in the final. Well, we'll use this 5% to bump up your grade because your trajectory is increasing, right? Okay, more on homeworks and labs. Do the homeworks to truly understand the material. Contents will be from lectures, readings, labs, and discussions. They must be your own work. You can discuss the homeworks with others, and I encourage you to work in groups, but the write-ups need to be individual. Okay? And no late homeworks are accepted. Too much to deal with late homeworks. Labs, and these will take time. You need to start early, and I already told you this. Labs will be done individually unless specified otherwise. You'll learn a lot more. We received a lot of good feedback from last year's students that individual labs may allow them to learn a lot more the material. In fact, several people stated specifically that they wouldn't have learned the material as well if they didn't do the labs individually. So I'm going to keep it the same way. And you'll have a total of 5 late lab days per semester allowed. So you can figure out how to distribute them. Okay, this is not the nicest of the topics, and I think you're all adults and I will treat you so, which means that absolutely no form of cheating will be tolerated. And I'm very harsh on that. We've had some unfortunate cases, not in this class, but in some other classes. And hopefully we'll keep the record nice, clean in this class so that we don't have a black spot. So basically don't cheat. You can see the syllabus, CMU policy, NEC, academic integrity policy. Cheating means failing grade. I will not make any exceptions, and perhaps more. It's a lot better to get a 0 on an assignment, work hard but not cheat, right, than cheat and learn nothing. So you're here for learning, and you're adults, so that's it. So homework 0, as I said, it's due next Monday, right before lecture. We'll collect that. Homework 1 will be due Monday, January 28th, right before lecture on Blackboard, and you will get that online. And this will be on warm-up for MIPS architecture, and hopefully you'll learn what MIPS stands for by the next lecture, and you can tell me when I ask the question. And it doesn't stand for millions of instructions per second in this context. It stands for something else. But hopefully you'll answer me when I ask the question. ISA concepts and basic performance evaluation. Lab assignment 1 will be a functional C-level simulator for a subset of the MIPS ISA. Am I already over time? No, not yet. It's due Friday, February 1st at the end of the Friday lab. Again, start early because this will be the first lab. And homework 1 and lab 1 are synergistic. Homework questions we'll try to do it such that homework questions are meant to help you in the lab. Okay? So readings for next time, I've already told you what these are. Yale PATS, requirements, bottlenecks, and good fortune. And it's our paper on memory performance attacks. And I've given you a good overview so that you won't start out cold. There are also some readings from the books that I would recommend. This is Pat and Patel, Chapter 1, Fundamentals. Patterson and Hennessy, Chapters 1 and 2. And you don't need to read this. And I certainly don't expect you to read the x86 reference manual. not for Wednesday, at least. But these are actually one of the best ways of learning about computer architecture, looking at these reference manuals and understanding how things are implemented. They don't necessarily give you the design trade-offs, but some reference manuals actually do give you the design trade-offs. And I'll give you examples of some of these reference manuals in the course also. But this is reference material throughout the course, so it's not readings for next time. I guess they're classified under the wrong title. Okay, there are no books required. This is, I think, my last slide. But I will assign you readings, and I think I'll expect you to be resourceful in finding and doing the readings. Sometimes we will provide scanned copies, but I cannot provide you the entire scanned book. But I don't want to require an entire book also, because there's really no book that covers the material that I would like to cover in this course. First of all, there's no really up-to-date book that covers all of the material as I will present in this course. So your lecture notes and the readings that I will assign to you will be the main source. But I will also assign you readings from the books that will help you with the both lectures and the assignments. And the hope is that you will be resourceful enough to figure out how to get to those. I have another story about resourcefulness, but we'll delay that for, for some other lecture. That said, we will have the books on reserve on the library, so that will be one way of getting to those books. Okay, and in the recitations, we'll cover the MIPS ISA tutorial next time, and times will be determined. So Justin, Yungu, and Jason will be doing that. I guess any questions before we part? All right. I'll see you Wednesday.